All right, welcome everyone. I am JJ. Let's go ahead and tackle an example problem. So we have our frame shown here. We have members A, B, B, C, and C, D. Is externally supported by a pin at A and a fixed support at D. And then we pin them together at B and at C. And we want to figure out what's going on at every location, A, B, C, and D. So if we start this one out, kind of our first step in a frame problem is to say, do I have any two force members in here? Members with forces at only two locations. So if we just count that off, A, B has forces at A and at B. But we also have this triangular distributed load. So we have forces all along here, not a two force member. BC has things at B, C, and our distributed load, three locations, or actually it's an infinite number because of our distributed load, not a two force member. CD has things at C, D, and we have our force and moment in here. Not a two force member either. So we can't deal with that one either. There's no two force members in this. Which means we move on and say, can I draw a free body diagram of the entire object and try to find anything there? So if I look at this, I would be cutting through A and the fixed support. B and C will get internalized into this, so I don't need to include BX, BY, CX, or CY on an overall free body diagram. But still counting my unknowns off, I would have AX, AY, DX, DY, and a moment at D. 5 total unknowns. That's way more than I can deal with. There's no place I will always have 2 unknowns in the Y, AY, DY, 2 unknowns in the X, AX, DX. There's nowhere I can sum moments and get rid of 4 of my 5 unknowns. MD is always going to show up in my moment equation. It'll be there no matter what I do. I can't do anything with that overall free body diagram. So we start looking at which pieces could I go to. So if I went to member AB, I'd have 4 unknowns there, AX, AY, BX, BY. I can't find everything. Could I find anything? Well, if I sum moments at A, I still have BX, BY. If I sum moments at B, I'd have AX, AY. No matter what I do, I'm going to have too many unknowns to solve this out. If I go to CD, I'd have CX, CY, DX, DY, MD, 5 unknowns. I definitely can't work with that. What if I went to BC? If this doesn't work, I'm going to have to set up a system of equations, and it's going to be awful. But if I go to BC, I still have 4 unknowns here, but I could sum moments at B. I get rid of BX, BY, and CX would pass through that. I'd be able to find CY. If I can get CY, I can sum forces in the Y. As soon as I know C or BY, well, now on AB, I'd then be down to AX, AY, BX. I can solve this one out, come in and get CX, and go to my very last member in there. So that's kind of that path we're going to take. Even though I can't find all of them immediately, let's come in and make a free body diagram of BC and see what we can find. So I'm working with member BC to start this out. Our free body diagram. It's just a nice horizontal member. At B, let's go ahead and guess that I have BY comes down. And that my BX, I'll guess it goes to the right. BX. Over at C, I'm going to guess that CY comes down. And that CX goes to the left. And then all the way along here, I have a distributed load. So we stick that in. It's a nice rectangle for us. Despite what my picture kind of looks like there, that should be a rectangle. And I know the height of this is 300 pounds per foot. 300 pounds per foot. And my width here is 12 feet. 12 feet. Again, 4 unknowns. I can't get everything here, but I should be able to get BY and CY out from that. So let's just start and do moments. With positive going counterclockwise, I'm going to sum my moments up about point B. That's going to get me, well, that distributed load will be counterclockwise. If I'm dealing with a distributed load, I need force times distance still to get a moment. The force, though, is the area of this. The area of a rectangle is base, 12, times my height, 300. Times a distance. I have force right now from the area. I need distance. My distance from B to the centroid of my rectangle. Well, the centroid of a rectangle is the very center of it. So from B to the middle, I go in half times 6. If that didn't start at point B, I'd have to first get to the rectangle and then go halfway in. But we're going to go on this one. CY will cause a clockwise rotation, so minus its moment, minus 12 CY, gets us to 0. Which I can solve that one for CY. I'll get that CY is 1,800 pounds. 1800 pounds. We're going down. And this was an internal connection here, so I want to specify which member. On BC. On BC. If I know CY, I can now either sum moments here at C, or I can sum forces in the Y. Let's do forces in the Y. If I sum up my forces in the Y direction, I have that distributed load goes up. I'm dealing with just force, so I only want area in here. Base times height, 12 times 300, minus CY, minus 1,800, minus BY. Should get us to 0. Or we're going to get our second answer. BY is also 1,800. 1,800. It's also, I get a positive number out for this BY, which means I guessed the right direction. It's going down. Down on BC. That's my second answer. Anything I do here, I can't sum moments anywhere and get only BX or only CX in the equation. Summing forces in the X, I'd have BX minus CX equals 0. And a common mistake I see students do is when they get that equation set up, I'm going to write it out really quick. I'll erase it in a second. But summing my forces in the X is BX minus CX equals 0. Every year I see a handful of students say, oh, if BX minus CX is 0, there's nothing else in the X direction here. That means they're both 0. That is not going to be true for us in here. This equation, that could be what ends up happening, but this equation actually solves to tell you BX equals CX. 0 could be equal to 0, but that's not the solution to that one equation. We have one equation and two unknowns. It couldn't be solved right there. Instead, we need to wait, and we'll come back to that. But I have BY. That means if I come over here to AB, I would have BX, AX, AY. So we'll abandon this free body diagram for now. We'll come back to it to get CX. But let's come in here and say, well, let's draw out AB. We're kind of going to bounce back and forth between our free body diagrams as we tackle this. So setting this one up, we have a L shape. At A, I'll put in AY for our pin, so it should go down. And I'll guess AX goes to the right. I have a triangular distributed load here, so we'll get that in there. It is pointing to the right, and my max height is 450 pounds per foot. And I know my height of this is 6 feet. 6 feet. My base is 8 feet. And finally, I know at point B, I can connect in BX and BY. They should be equal and opposite. So first off, I have a BY went down originally. I had it down on BC. That means opposite. It should be going up. But equal, it still is 1,800. And I left off my units in here. Pounds on BC. So 1,800 pounds. On BX, I guess it went to the left. Let's make a consistent assumption as we tackle this. If it's, or I guess it went to the right, which means here it's opposite. It should now be going to the left. Three unknowns, AX, AY, BX. I can use equilibrium and find all three of these out. So let's go ahead and tackle this. Let's go ahead and do moments about point A to start out. With positive, going counterclockwise, summing my moments about point A is going to get me to, well, I have my 1800 BY will cause a counterclockwise rotation. So that's 8 force is 1,800. My distance is 8 feet times 8. My distributed load, it's all below A, so it's going to push to the right down below, cause a counterclockwise rotation. So we'll add in plus our force component is the area, 1/2 6 base times height, 450. That's just area right now. For moment, I need a distance. And my distance for a triangle should be 2/3 from the pointy side. So the pointy side is at A. I can immediately go 2/3 of 6 into this. So times 2/3 times 6, or just times 4. It's really that 6 is our distance we're getting here. 2/3 just shrinks it down a little bit. Don't just multiply by 2/3. That's a coefficient in here, not a distance. But times 2/3 times 6 gets us, we're 4 feet in, right about here. But then our last one is bx will be clockwise. It's 6 feet below, minus 6, bx gets us to 0. Or solving for bx, I'm going to get here that bx is 3,300 pounds. 3,300 pounds. And that was going to the left on, remember, BC. On AB, which is our third answer. We could at this point go back to BC. I can now find CX. We'll do that in a bit, but let's go ahead and finish up this free body diagram, get everything we can here, and then we'll bounce back a little bit. But I can now, if I know BX, I can just sum forces in the X and the Y. If I sum my forces in the Y direction, I have BY going up, 1,800, and AY comes down, minus AY, gets us to 0. There's nothing else in the Y direction here. So AY has to end up being 1,800 pounds, and it is going down. I get a positive out from this equation, so I guess the correct direction. With AY known, or before here, I could have sum force in the X, and we would get AX out. Or I can do moments at B, and I get AX out. But forces is typically easier. If it's easier, we're less likely to make a mistake. Let's play to our strengths in here and not make mistakes. So summing forces in the X, I have AX plus the area of my distributed load, plus 1/2 base 6 times height 450 times, or not times anything, I have BX in here, minus BX minus 3,300 should get us to 0. Where AX is our only unknown, if I solve for AX, I'm going to get that it is 1,950 pounds, and it's going to the right. So I got 3 unknowns from free body diagram AB. I've only gotten 2 unknowns out from BC, but I found BX, which means we can come back up here and do BC again. BC again. And it's just summing forces in the X is all I need to do here. Summing my forces in the X direction. I have, well, BX went to the left here. I made a consistent assumption. So if it's to the left here, I know it is really to the right on BC. Changing that direction as I move from one member over to the next. So it's positive 3,300 minus CX gets us to 0. Or solving for CX, it's also 3,300. CX is 3,300 pounds. And it's going to the left on BC. On BC. Which would be our next answer. That's now 3 unknowns I've gotten from AB and BC. I can't do anything else with those. So I need to either make a free body diagram of the entire frame. That would get me there. Or I could come in and say, why don't I just make a free body diagram of CD? I know CX and CY. I'll have to carry them forward. But it's going to be way easier than making a huge free body diagram to deal with. I get just one straight line. There's no distributed loads. It'll be easier. Take the easy approach. So we're looking at CD. D, not B. CD. And I have a stick line for my free body diagram. I know at the bottom of this, I have CX and CY. CX was 3,300 to the left on BC. I'm moving to a new member, so it should be equal and opposite. New direction, but still 3,300 pounds. CY was 1,800 going down. I'm moving to a new member, so it should change direction. It's going up 1,800. That's the direction changes. That's our opposite in Newton's laws. There's an equal and opposite reaction. The magnitude stays the same. That's the equal part in equal and opposite reactions. Basically, the pin itself, if we drew a free body diagram, will be in equilibrium. But we can come in here and say, if I go up 3 feet to the middle of this, there's a 1,500 pound force. 1,500 pounds. 3 feet more gets me to the top. But also right there in the middle of this, there's a couple moment being applied. So it's going clockwise, 2,500 pound feet. And then I can get up to the very top of this at point D, where I have 3 reactions that I need to find to finish up the whole problem. I can get in a dy, should go straight down. I can get in a dx, goes over to the left is what I'm guessing. And fixed supports resist moment. Again, don't forget that. I will almost always on my exams put in a fixed support problem, and I wreck people's grades if they leave that off. We got to be able to get our free body diagrams right. But I'm going to assume this goes clockwise. We get an MD variable in there. 3 unknowns at D, we can get all of them. Let's go ahead and get MD first. With positive, going counterclockwise, let's sum up my moments about D. That will eliminate dx and dy from this. I have MD as my only unknown, and I got to put that in as a variable in here. MD is the variable I'm finding. It has to show up in my equilibrium equation. Otherwise, I'm not actually adding everything up to 0. I'll get the right magnitude, but I get a sign error coming out from everything. Let's look at it. CX causes a counterclockwise rotation. So MD plus, actually I assume this is clockwise, so negative, plus force is 3,300 times my distance, 3 plus 3 is 6. My 1,500 will cause a counterclockwise rotation. So plus 1,500 times my force is 3. And my couple moment is clockwise. So minus 2,500 gets us to 0. If I solve for MD, this is one of my external supports. I just need to say magnitude and direction, not on a member. But I'm going to get that my moment that fixed support D resists is, this will give me a positive number coming out. So I guessed the right direction. It is clockwise, 21,800 pound feet clockwise. And then I can go on and do forces in the X, forces in the Y. My forces, we're actually going to do Y first. Forces in the Y should be 1,800 coming up from, that was CY minus DY. I guess went down, gets me to 0. DY is also 1,800 pounds. And then finally, the one last thing that we need to get in here is just sum our forces in the X. Summing forces in the X direction. I have CX 3,300. I have 1,500, our applied load, minus dx. Gets us to 0. Or our very last answer in here is dx equals 4,800 pounds. Again, this is an external support, so I just say or which direction. We don't change the direction around because we never move it to a new member. But hopefully this is a useful video for you. If it was, hit those like and subscribe buttons. Stick around, watch more videos. Let's get you in A with JJ.